Hello everyone, I am Alif bin Abdul Qayyum and my co-author is A&M Nafiz Abeer. Both of us are PhD students at Department of Electrical and Computer Engineering at Texas A&M University, College Station, Texas. I am going to present our work, Physics-Informed Model-Based Reinforcement Learning for Controlling Synchronization of Weakly Coupled Kuramoto System. This work has been accepted to the third Muslims in ML workshop co-located with NeurIPS' 2024. Kuramoto model is a representation of collective dynamics such as neurobiological systems. Kuramoto, it is a network of different oscillators coupled with each other through a coupling coefficient value, and the behavior of the overall model is governed through a bunch of coupled differential equations. Usually, when the coupling coefficient of the overall Kuramoto model is lower, then it is a weakly coupled Kuramoto model and it tends to behave in an unsynchronized manner. To control the overall Kuramoto model, we need to apply control signals to each of the oscillators. However, controlling such a complex system like Kuramoto model is challenging due to various reasons. For example, if we want to apply control signals to one specific oscillator and try to synchronize it, it might disrupt the frequencies and phases of the other oscillators, and the overall system may get unsynchronized. Also, when the overall Kuramoto model is larger, there are a large number of oscillators in the model. It's more difficult to control such a model. We use reinforcement learning for this problem, and the overall reinforcement learning problem formulation looks like this. We have an environment, in this case is a Kuramoto model. The states of the environment are the angular phases of all the different oscillators. We have an agent that tries an action, and the action in this case is the control signals to each of the oscillator. After applying the control signals, the phases of all those oscillators change, and the overall synchronization status of the environment changes. And from the synchronization status, the agent gets a reward depending on the synchronization status of the overall model. And that's how the overall reinforcement learning problem formulation work for this work. We used three different kinds of reinforcement learning approaches. The first one is a model-free reinforcement learning. So here we don't have any model that tries to imitate the underlying environment. In this case, it is a Kuramoto model. We used twin-delayed deep deterministic policy gradient method to train the agent. We also used model-based reinforcement learning, where we have a model that tries to imitate the environment, in this case, which is a Kuramoto model. And we use generated data from that imitating model and also the data collected from the actual environment to train our agent. Usually we use reconstruction loss between the generated data and the collected data to train the imitating model. In the physics-informed model-based reinforcement learning case, we use physics-informed residual loss apart from reconstruction loss to imitate the environment, aka the Kuramoto model. The goals for all the experiments done in this work is to enhance the sample efficiency. That means we want to use lesser number of samples or explorations to train the agent so that it can take optimal action or it can apply optimal signals to control the overall Kuramoto model. We use two different kinds of Kuramoto models, one with 5 oscillators and another with 10 oscillators. To make the uncontrolled Kuramoto model unsynchronized, we use a low value for the coupling coefficient, which is 0.01. These are some results. Here, the RM value shows the ratio between the generated data by the imitating model and the data actually collected from the environment. And we can see that both the regular model-based approach and the physics-informed model-based approach outperform the model-free approach. These results are for a smaller network with 5 oscillators. For a larger network, we can see that the highest reward got by the agent becomes less frequent compared to a smaller Kuramoto model with 5 oscillators. For a larger network, what we see is for some cases, when the ratio between the generated data and the collected data is smaller, all the different reinforcement learning methods perform quite similarly. However, when the ratio gets higher so that we are using more synthetic data, those data generated by our imitating model, our proposed physics-informed model-based reinforcement learning method outperforms the other two methods. So the key takeaways we can say in this work is for a smaller network, the regular model-based reinforcement learning and the physics-informed model-based reinforcement learning perform quite similarly. However, for larger network, having a physics prior actually helps to learn taking better control strategy. For future exploration, we would like to see whether using a generative model to imitate the underlying dynamics works better or not. So thank you, everyone. These are the two contact points for both of the authors. Please feel free to reach us if you have any questions.